IIT College of Engineering, Kolhapur. Today we are here to discuss on the course Advanced Design of Concrete Structure. First of all, we discuss about the broader objectives of the course. First is identify the provisions made in IS 456-2000, IS 3370-1984 and IS 1346. Second, develop the concept of yield line theory. And third, analysis and design of different structural elements, water tanks and retaining walls. So today we discuss on unit number 1, that is flat slab, and lesson number 5, solved problem on external panel of flat slab up to moment calculations. The objective of the lesson is analysis and design the RCC structural elements such as flat slab. Up till now what we discussed about the introduction of flat slab, advantages, disadvantages, then the analysis method of flat slab, that is direct design method, and second is equivalent frame method, and then we discussed the design procedure of internal panel, design procedure of internal panel of flat slab and design procedure of external panel of the flat slab. Now we are here to solve the problem on external panel of the flat slab. Now see, this is a problem. Work out the moment distribution of external panel of a flat slab of size 5 meters by 5 meters with suitable drop to support live load of 3.8 kilonewton per meter square. The floor is supported by columns of size 380 mm by 380 mm. Use M25 grade concrete and Fe415 grade steel. Take the column height is equal to 4.25. Now this is a given data to you. First of all, write down the given data. L1 is equal to L2 because the slab is square slab, that is 5000 mm. Live load is 3.8 kilonewton per meter square. Column size is 380 by 380 mm. FCK 25 Newton per mm square. Fy is equal to 415 Newton per mm square and column height is 4.25 meters. This is the given data to you. So your first step is work out the depth or work out the width of column strip and middle strip in both direction. Now here the problem is very easy because the given slab is square slab. Whatever you are going to do the calculation in one direction, you can repeat the same values in the another direction because the slab is square slab. Now first step is work out the column strip, width of column strip and width of middle strip. So width of column strip is equal to 0.5 L. The ratio is 0.25 to 0.5 L. We are considered here 0.5. So 0.5 L is equal to 2500 mm, 2500 mm. The width of column strip is 2500 mm and width of middle strip is again 2500 mm, 0.5 L. Next step is work out the effective depth provided. So what is the ratio or what is the formula? The formula is L by D is equal to 32. Now why 32? Because drop is provided. If drop is not provided, then L by D is equal to 40. This ratio should not be less than D provided. So 5000 divided by 32 is equal to 156 mm. This is a calculated depth 156.25 mm. This is the effective depth which is calculated. Next, assume the effective cover 35 mm. Assume the thickness of slab or thickness of drop is equal to 55 mm. Therefore, the overall depth of slab is equal to D, capital D is equal to small d provided plus effective cover plus drop is equal to 256 mm as 246 mm. So make it round 250 mm. Now your next step is calculate or load calculation. First of all, calculate the self-weight of slab. Self-weight of slab is equal to capital D into rho D, that is density of concrete. So what is the depth? Depth is 250 mm, which is calculated in the above step. So 0.25 into 25, what we get? We get 6.25 kilonewton per meter square. Live load is given in the problem, that is 3.8 kilonewton per meter square. Hence the total load is equal to 10.05 kilonewton per meter square on a external panel of the flat slab. Then make it factored. So multiply it by a factor of safety 1.5. So 1.5 into 10.05 we get 15.05 kilonewton per meter square. Then calculate the total load on the slab is equal to factored load multiplied by L1 multiplied by L2, that is 15.05 multiplied by 5 multiplied by 5. The total load is 376.8 kilonewton. Now next is you want to calculate the coefficients for moment distribution of external panel. So for that some basic calculations are required, that is length of column LC is equal to column height minus overall depth. So column height is 4.2 which is given in the problem, minus overall depth of the slab, that is 0.25. What we get? We get 4 meters. Next, assume both ends of the column are hinged. Hence, the effective length of column is equal to 1.2 into LC, that is length of column is equal to 1.2 into 4, 1.2 into 4, that is 4.8. This is the effective length of the column. Now, next step is calculate moment of inertia for column IC, which is denoted by IC. IC is equal to BD cube by 12. We get 1.73 into 10 raised to 9 mm raised to 4. Then calculate flexural stiffness of column Kc. Kc is nothing but flexural stiffness of the column. Kc is equal to Ic upon effective length of the column, that is moment of inertia upon effective length of the column. So what we get? We get 360.4 into 10 raised to 3 meter mm cube. This is the moment of inertia, and this is the moment of inertia. See, IC, this is the moment of inertia. The value is 1.73 into 10 raised to 9, and Kc is nothing but the flexural stiffness of column, which is 360.4 into 10 raised to 3 mm cube. Next thing, moment calculations. Now for that, first of all, you want to calculate the moment of inertia of slab, that is denoted by Is. So Is is equal to L by D cube upon 12. L is nothing but the span of the flat slab, that is 5000, into B is the D is the depth, overall depth of the flat slab, divided by 12. We get 6.51 into 10 raised to 9 mm cube. Then flexural stiffness of the slab, that is Ks, Is upon length. So 6.551 into 10 raised to 9 divided by 5000, we get 1.30 into 10 raised to 6 mm cube. Now by using this Ks and Kc, Ks is what? Flexural stiffness of slab, whereas Kc is what? Flexural stiffness of column. So by using these two, you want to calculate the relative stiffness of the relative stiffness ratio of the column, which is denoted by alpha c. So alpha c is equal to 2 Kc upon Ks, that is twice the flexural stiffness of column divided by flexural stiffness of slab. So alpha c, what we get? Alpha c is equal to 0.55. Next, calculate relative stiffness ratio for slab, which is denoted by alpha s. So alpha s is equal to 1 plus 1 upon alpha c. Alpha c is what? Relative stiffness ratio of column. So 1 plus 1 upon 1.55, what we get? We get 2.81. This is the basic calculations, whatever we required to calculate the coefficients. Now henceforth we are going to calculate the coefficients which are required to distribute the moments into column strips and middle strips. So first coefficient C1, internal negative moment coefficient, which is denoted by C1, and the formula is 0.75 minus 0.1 upon alpha s. What is alpha s? Alpha s is relative stiffness ratio of slab. So C1 is equal to 0.75 minus 0.1 upon alpha s, that is 0.75 minus 0.1 upon 2.81. What we get? We get the C1 ratio is equal to 0.72. Second is external negative moment coefficient, which is denoted by C2, and the equation of C2 is equal to 0.65 into alpha s. So 0.065 upon 2.81, we get C2 is equal to 0.23. Third and last coefficient C3, which is known as positive moment coefficient, and the formula is 0.63 minus 0.28 into alpha s. What is the formula? C3 is equal to 0.63 minus 0.28 upon alpha s. So 0.63 minus 0.28 upon alpha s 2.81. What we get? C3 is equal to 0.53. Now these three coefficients are most important to distribute the calculated moment or total moment into column strips and middle strips. Next, how to distribute the moments into column strips and middle strip. Okay, see the table, or first of all calculate the total moment on the external panel. Total moment on the external panel, that is m naught is equal to total load on the flat slab multiplied by span of the flat slab divided by 8. So what we get? We get total moment is 235.5 kilonewton meter. This is the total moment acting on the external panel. Now first of all you calculate the factored moments. Prepare the table. First column is moment, second column is factored moment, third column column strip, fourth column middle strip. Now see the row wise. First row is what? Internal negative moment. What do you want to find out? Find out the internal negative moment. So first of all calculate the factored moment. The equation of factored moment is what? Mn is equal to C1 into m naught. Mn means what? Internal moment. Internal negative moment is denoted by Mn, and it is equal to C1. C1 is the first factor, first coefficient which is calculated in the above step, into total moment, that is 0.72 into 235.5. What we get? We get the value 169.56. This is the moment which is acting on the internal negative moment, or this much moment is act in the internal panel or internal moment, negative moment. Now this internal negative moment you want to distribute into column strip as well as into middle strip. So what is the distribution factor? The distribution factor is 0.75 for column and 0.25 for middle strip, which is already discussed. So this internal negative moment multiplied by 0.75, we get 127.1. This is the moment acting in a column strip, whereas 42.39 moment is acting in the middle strip. These are the negative moments acting internally. Now always remember that negative moment act at the top face or top extreme fiber of the slab, whereas the positive moment are act at the bottom fiber or extreme bottom fiber. So these are the negative moments which are distributed in the column strip as well as in the middle strip. Second is external moment or external negative moment. ME is equal to C2 into m naught. C2 into m naught. C2 is the coefficient of external moment. So coefficient is 0.23 multiplied by the total moment 235.5. What we get? We get The total external negative moment is 54.16 kilonewton meter. Now this 54.16, you want to distribute this moment into column strip as well as in the middle strip. Now as per the provisions, the total external negative moment is act in a column strip. There is no external moment acting on the middle strip. Hence, whatever the external moment we get in the second column, write the same value in the third column, that is column strip moment. Last thing is calculate the positive moment which is acting on the column strip and middle strip. So first of all, calculate the factored moment. Positive moment is equal to C3, that is coefficient of positive moment multiplied by total moment. So coefficient of positive moment is point again 23 multiplied by 235.5. What we get? We get 124.8 kilonewton meter. This 124.8 is again distributed into column strip as well as in the middle strip. So what is the distribution factors? 0.6 is for column strip and 0.4 is for middle strip. Means what? The total moment, whatever positive moment is there, the 60% of moment is acting on the column strip, whereas 40% moment is acting on the middle strip. So what is the value of positive moment in the middle strip? 0.4 into total positive moment, that is 0.4 into 124.8. What we get? We get 49.92, and the positive moment acting at the middle column strip is 0.6 into MP is equal to 0.6 into 124.8, we get 74.8. Now this is the typical example of external panel up to moment calculation. In the next lecture we are going to discuss how to design the reinforcement. Okay. So we will stop here and we will discuss the reinforcement design in the next lecture. Thank you.